Hello, welcome to our weekly starter video. We're in Module 1. It is week 2 of the term, and we are going over the scientific method, and we're going to use these guys right here, barn swallows, as a quick case study of the scientific method. So big picture stuff, I want you to understand the steps in a scientific method and how they relate to one another. Understand how to develop a question and form a hypothesis, how to design an experiment that tests that hypothesis, and then the elements of a well-designed experiment, including controlling the variables. So before we jump in, we're going to go over a couple science things. We're going to use that as a case study, but I don't want you to feel like you need to know exactly every single thing about barn swallows. We're using these guys as a case study to showcase the scientific method. So pay more attention to the scientific method itself than to the actual study itself. So our story begins with these guys, the barn swallows. Some Swedish scientists about 30 years ago started asking questions about them. One of the questions they asked is, how do physical features play a role in animal behavior, specifically mate selection? And they began with observations and asking questions about observable phenomenon, that stuff that we can see. Tail length. As you notice, those barn swallows have those very, very, very forked tails that are easy to see. When you look at them, they kind of capture the eye. And so they wanted to know, how do those play a role in how many offspring males have? And so their question was, how does tail length affect reproductive strategies? I want to give a word of caution about how we think about science. So it's really easy, even in our text, there's a kind of step-by-step form of the scientific method. Ask a question, develop a hypothesis, create an experiment. That's great, and that's helpful for us when we are trying to make an experiment and trying to design an experiment. That's a really nice cheat sheet to have with us as we do that. But science as a whole, we're never doing science in a vacuum. So this graphic on the left is a really good way of looking at and thinking about science. So anyone who's studying barn swallows, there's probably hundreds of scientists throughout the world that are studying birds, and some of those are studying barn swallows. So you have a whole community that you're helping develop a pool of knowledge about. So I like to think of this as this exploration and discovery, just asking questions and curiosity is a piece, testing ideas. If there's benefits from that, great. And then community analysis and feedback. So this is not just happening in your lab or with your group or your team or whatever. This is something that's happening on a global scale. We communicate as scientists with each other all over the world. And I want you to think about it as a community of people that are building a knowledge base so that we have a better understanding of the world. Not to what our image on the right says. I think you should be more specific in step 2 is what the instructor is saying. No, it doesn't really happen in a vacuum. Before we jump into the barn swallow example, I want to give you a quick note on writing a hypothesis. We've got to get rid of the if-then format. So it deals with correlation and causation, and it's a very narrow way of writing a hypothesis. I'm going to show us a good way of doing that, a good way of writing it. It really limits the scope, but here is our weekly starter quiz. So each week you'll have a weekly starter video, and then you'll have one question about something in the video. And here's our answer right here. A hypothesis, to be a good hypothesis, it has to be falsifiable and it has to be testable. And we'll play around with all this stuff in our live class. But it has to be those two things. So here's our case study with barn swallows. So those Swedish scientists have been studying barn swallows for a long time, and 35 years ago they got together, wrote a paper, and then submitted it to Nature, which is kind of a big deal in the scientific community. But their first thing was just questions and observations. They observed that male barn swallows have that significantly long tail than female barn swallows. So their question is, does the length of a male's tail influence a female's choice of mate? And when we get into animal behavior and ecology, we'll hear this idea of female's choice over and over and over again. Typically, if you ever see a really unique structure on an animal, it's typically going to be a male, and we'll talk more later on in the year about female choice. But that's something that you'll notice, is that males tend to have those structures or those physiological traits that you can easily see. So next, once we've got that observation, that question for this specifically, how we're going to design an experiment around figuring this out, is we have our hypothesis. So it's testable and it's falsifiable. Male barn swallows with long tail length will produce more offspring than males with shorter tails. So we have our two things. We have something that's falsifiable, because we could prove it false. If male barn swallows with long tails produce less offspring than males with shorter tails, we've proven it false. So it's falsifiable. We have a way of proving it false, and it's testable. It pretty much sets up what our experiment's going to be. And I want you to not really worry too much about the details of their experiment. It gets a little complicated, but there's an experimental group and a control group. And our experimental group is the group that we're experimenting on, and our control group is the group we keep the same to make sure that whatever variable we are changing is the one that it is causing our dependent variable to change. So our experimental group is gluing long feathers to a normal bird's tail in one group and clipping short tails on a normal bird's tail feather. And so we've elongated them, and then we've cut them short. And then we've got a couple groups that we've just got normal tail length. And that's what an experimental group and a control group is. We'll get into this more this week. I don't want you to feel like you have to master everything today from our weekly starter, but just an interesting case study of the scientific method in action. So we got to sort out what's our independent and our dependent variable. The easiest way to think about it is our independent variable is the variable we are manipulating, and the dependent variable is the variable we're measuring. So hopefully you can see tail length is our independent variable, and number of offspring, that's what we're measuring, is our dependent variable. When it comes to data and analysis, we just have to look at our data and ask the question, did manipulating our independent variable change the dependent variable? And the analysis comes from answering that question and using the data to answer it. And then there's two kinds of data that we can work with in an experiment: qualitative data and quantitative data. Qualitative data is something that's not necessarily a number that's more difficult to count. It's more of a description. So the type of fur, whether a mouse has smooth fur or it has rough fur, that's qualitative because we can't explicitly count it. But quantitative data are number of eggs that are laid. That's a quantitative number. That's something we can count, write down a number for. So I always think of quantity as counting. Quantitative data is something that's counted and it's represented numerically. And if we look here, we see our independent variable is either a longer tail, a normal tail, or a shorter tail, and then our number of offspring. This table up here gives us kind of our hypothesis written in table form. If it has a longer tail, it's going to have more offspring. A normal tail, average number; shorter tail, smaller. If you look down here, you can see the actual data from Nature, from the paper they published. And there's a couple interesting things. Our tail length is our independent variable. That's what we manipulated. And the number of offspring for an elongated tail, a tail that was made to be longer, 8 offspring. A normal tail, 5 offspring. A re-glued tail, 5 offspring. So we've got our elongated tail and our re-glued tail have a different number of offspring. And then a shortened tail only has 3. And so this is probably going to create new questions. And this is where we see that kind of circle of the scientific method. And so we've got a general answer to our question, but there's still different avenues that we can explore. And so this is that idea that the scientific method might help give us an answer when we go through the experimental process. It might help give us an answer, shed some light, but then there's going to be new questions that are formed. And so you're going to go through this process again and again, just to try to paint a bigger, more detailed picture about what's going on. Lastly, I wanted to go over observation versus inference. We're going to have a lot of fun examining these in class. So I just wanted to quickly give you the definition of an observation, the definition of an inference, and then we'll play with what these are like and how we experience them as humans in class. But an observation is using one of our five senses to gather information. So if I see something, if I hear something, that's an observation. An inference is using logic and your prior experiences and your consciousness to interpret that. So let's say you're listening to music. An observation would be, if you can read sheet music, saying what kind of chord. That's a major chord, that's a minor chord. There's consonants, there's dissonance. If you're not a musician, you don't have to worry about that example. But an observation is just simply looking at something and describing what it is you see. An inference is using logic to interpret what you think is happening in a situation. Not the picture, but what you think the picture means. We will dive into this and more during our first week together. Anyways, that's it for now. I'll see you in class.